we'll spend some time on little mathematics here. So let me take the pulse train again. My pulse train is something like this. Let us suppose. I'm taking a symmetric pulse train on either side. Sorry. Let it be C of t is 0. Okay. Of course, the width of the pulse is tau. Okay. And from here to here is my fundamental time period. Let it be capital T. What else? Amplitude. Let it be A. Now the question here is, I want to represent this C of t in Fourier series. So in C of t in Fourier series, if I want to represent, either I need to calculate A naught, AN and BN, right? These are the coefficients. AN and BN are the coefficients of sine and cosine terms. A naught is a constant value. Now my question is, which type of function is C of t? C of t can be we can minimize this using that what we call it as um, even odd functions, right? Even and odd functions. Okay. So can you anyone tell me what is C of t? Whether it is even function or odd function?
Symmetric about y-axis is even.
So because it is symmetric about y-axis, perfect. Your answer is correct. My C of t is even. Now what happens if C of t is even to the coefficients of Fourier?
It contains only constant and cosine terms.
So Pn is 0, right? This is what you want to say. Bn is 0.
Yes,
right?
sir.
Excellent. So considering the advantage of even function, so I just want to express this entire C of t, whatever we have used this pulse train. So I want to express in terms of Fourier series. Okay. So for that, have little patience, we'll get everything. Let me calculate the A naught value. A naught is 1 by t integral of I think minus t by 2 to t by 2. Okay. C of t dt. Then, so I have to, that means minus t by 2 from here to here is one time period, right? From here to here. C of t amplitude is A. So this can be rewritten as minus t by 2 to t by 2. So from here to here anyway it is 0. So this point my limits can be further simplified as minus tau by t2 tau by 2. So this will be equal to 1 by t fundamental time period tau by 2 to tau by 2 c of t amplitude is a into dt. Can you evaluate this integral and tell me? You all know integration, I think.
A tau by T.
A?
A tau by A tau by T, sir.
Perfect. A tau by t. Let it be, let me change t as ts, sample time, so that this will be ts, ts, and this will be ts. Yeah. So a tau by ts is my a naught value. Fine. Then let us move to the calculation of an. An equal to, I think by definition it is 2 by ts integral of minus t by 2 to t by 2. Okay. C of t into cos of n omega naught t dt. So can you please evaluate this integral? So C of t value I put as a minus t by 2 to t by 2. I change the integral limits, something 2 by ts integral of minus tau by 2 to tau by 2. A is a constant, so I put at the outside of the integral. So cos of n omega naught t dt. Now you evaluate this integral and put the limits and tell me what is the minimized expression. 2a by ts into, after integration I can get sine n omega naught t by n omega naught. Substitute the limits as minus tau by 2 to tau by 2. Substitute the limits and tell me. Here omega naught is 2 pi f naught, that is 2 pi by ts. Keep remember. Cover? You can substitute omega naught also. You can simplify and tell me. Simple substitution.
2a
Tell me the.
sin
Yeah,
2a
please.
sin of n by tau by ts by n by.
I'll write first this 2a by tau ts, 2a by ts. First one. So sine of n pi tau by ts divided by n pi tau by ts. If I put tau is not there, so I have to put a tau here. Is that correct? 2a tau by ts into sine of n pi tau by ts divided by n pi tau by ts. I multiplied and divided by with tau. That's all.
Yes, sir.
Okay. So this will be 2a tau by ts. What is this function?
Sir,
Sinc
value
function.
is not
Function, sir.
It is called sinc function, right? Yes, somebody is saying something. You did not get this value?
nothing, sir. I get it, sir.
Okay. So now we got a0 and an values, right? A0 is a tau by ts, an is 2a tau by ts, sinc function of n pi tau by ts. So C of t can be expressed as C of t can be expressed as now C of t equal to a0 by 2, that is a tau by 2 ts plus 2a tau ts into sigma n running from 1 to infinity. So all this is my an, so I put an only, cos 2 pi n t by ts. This is my C of t, right? Cos n omega t. 2 pi by ts is omega, right? 2 pi by ts is omega. Cos n omega t. That's all. Nothing complex here. And from the Nyquist criteria, we know that my Fs should be or greater than or equal to 2f naught. That is Ts is far less than T naught by 2. So for the time being, let us assume A equal to 0. Sorry, A equal to 1. The amplitude of the pulse or the height of the pulse is 1. So if that is the case, then what is your S of t? S of t is m of t into C of t. What is C of t? Just now we derived C of t is a tau by 2 ts plus 2a tau by ts into sigma an into cos 2 pi n omega t. Sorry, cos of n omega t. So let us assume a equal to 1. Now my S of t can be written as, I want to write my S of t as S of t equal to, after multiplying with m of t. After multiplying with m of t, my S of t can be written as something like this. tau by 2 Ts, A is 1. So A tau, A is 1 into M of T is my first term plus second term 2 tau by Ts into, so A is 1, so 2 tau by Ts into, put n equal to 1, then n equal to 2, then n equal to 3, so on and so forth. So then you will get A1 M of T cos of 2 pi T by Ts. Then, so if I put 1, n equal to 1, 2 pi T by Ts. Then so in terms of F naught or Fm, if I want to write worst case condition, my Fs equal to 2Fm, right? So 1 by Ts is Fs. So I rewrite this as this part. Let me rewrite it as considering this also into account. I rewrite that part as cos of 2 into 2Fm, that is 4 pi FMT plus second term A2 M of T cos of 6 pi FMT plus A3 cos of 8 pi FMT plus so on. Is that clear? Any mistake in the substitution? This will be 1, 2. I think this is 4, not 6. Will be 4, 2, 3, and this will be 6. Yeah. Is S of T clear? No reply. Hope you can hear me, right?
Yes, sir.
Is S of T clear?
Yes, sir.
Okay. So till now there is no doubt. Okay. Fine. Now, so we have represented S of T in terms of time domain by considering C of T representing in Fourier series. So finally we arrived at this. Now I want to represent this time domain expression in terms of frequency domain. So how to convert time into frequency?
Fourier transform.
Perfect.
Transformations.
So we need to apply Fourier transform, right? So after Fourier transform, we can convert the time domain representation of the signal into its equivalent frequency domain representation. So for the time being, assume m of t, its Fourier transform is, let it be m of f. Okay, m of t Fourier transform is m of f. Can anyone tell me what is the Fourier transform of m of t into cos 2 pi fmt? If m of t Fourier transform is m of f, what is the Fourier transform of m of t into cos 2 pi fmt? I think by this time you all know from your signals and systems. Multiplication with the cos. You can get it from shifting property, I think. Any guess? What would be my, what happens to m of f if I multiply m of t with the cos 2 pi fmt? No idea? Yes?
Y into delta of
M of f is shifted by fm. If m of t is multiplied with 2fm, 2 pi into 2fm, that is 4 pi fmt. Then m of f minus 2fm. So on and so forth. This is one of the property of the Fourier transform. Okay. So consider these things into account. Let us now apply Fourier transform to S of t. If I apply Fourier transform to S of t, forget about this constant. Tau by 2 ts is a constant. M of t Fourier transform is m of f. This is anyway constant. Tau by ts, 2 tau by ts. A1 is constant. M of f cos 2 pi fmt. Sorry, m of f, m of t into cos 4 pi fmt. Apply Fourier transform. So therefore, I rewrite my Fourier transform of the transformed signal can be written as m of f equal to, s of f equal to so t by 2 ts tau by 2 ts into m of f plus what would be 2 tau by ts into what would be the first term, a1 m of f f minus 2fm plus 2 tau by ts a2 m of f minus 4fm plus so on. So this is the time domain representation expression and this is the frequency domain representation expression. And finally, if I draw the waveform, if I draw the spectrum, I draw the spectrum. Let it be the spectrum of M of F, M of T is M of F. So let it be, it will look like something like this. Let us suppose this is FM, highest modulating signal frequency. This is minus FM. So now my naturally sampled pulse amplitude modulated signal spectrum will look like this. What is my first term? M of F into something. Forget about this. M of F into something. So I'll get M of F spectrum as it is. Then 2 tau by Ts. Okay, this is okay. A1 into M of F minus 2 FM. F minus 2 FM. This entire M of F is shifted by 2 FM. Where is my 2 FM? From here to here FM, from here to here 2 FM. So now I got my second term can be written like this. What is my third term? A2 into M of F minus 4 FM. This is 2 FM. This is 3 FM. From here to here, somewhere here, 4 FM. So I can have a spectrum like this. If you observe carefully, the M of F spectrum is decreasing. It will decrease something like this. The reason is the coefficients of A1, A2, and what are A1, A2? This is my AN. If n equal to 1, n equal to 2, this is a sinc function. Sinc function will look like this. So therefore, my sinc function will look like this. Therefore, my M of F magnitude also decreases. So this is the S of F. This is my S of F. Frequency domain representation of naturally sampled pulse amplitude modulated signal. Okay. So is that clear? Till now?
Yes, sir.
And here I have represented a switch. Here there is a switch. I'll take just 2 minutes to conclude. So that switch or a practical circuit can be drawn as. Let me take a simple CE configured amplifier. I have VCC. And this is my RC. Collector, base, emitter. So here I use emitter resistor RE. And this is my input M of T. So what I do is before giving M of T, here I give my C of T. Forget about M of T. When you give C of T is a pulse train. M of T is the message signal. So when C of T, the pulse amplitude is high, when it is at 5 volts, that means you are providing, this is an NPN transistor. So you are providing a 5 volts to the base. That means we are forward biasing this. So when base emitter is forward biased and you apply M of T, that M of T will appear across RE. when C of t becomes 0, my base emitter is not forward biased. So base emitter is open. Even you apply M of t, I will not get anything at the output. Therefore, my output will look like this. So as long as the pulse is there, I can get something at the output. When there is no pulse, we will not get the output. This is my pulse amplitude modulated signal. This is how we generate using a simple BJT circuit.